So hello and welcome to the online session of Introduction to Chemical Thermodynamics and Kinetics. Really to see the brief history of classical thermodynamics. So have to know about the what is physical chemistry or chemical physics. Okay, so there is an interaction between matter and energy. So if you use the energetics, this comes under the classical thermodynamics. So what is the energy change when we are changing some state, some phase, or some reaction is happening, whatever with respect to energy, it is dealt by the thermodynamics. And if we want to know about the change in rate, which is basically a time dependent parameter, then it is dealt by the kinetics. Yeah. So basically the macroscopic or phenomenological part, which is the time independent energetics, is the classical thermodynamics, and which is a time dependent rate, which is the called the kinetics. Okay. So in the energetics there is an equilibrium formalism, and it comes under the quantum chemistry, and this is defined by the quantum mechanics. So the question comes is, at what level do you want to understand or study this interaction? Okay. You can think of energetics, which is a time independent process, or you can also talk about the kinetics, as I told, or how this exchange of interactions is happening with respect to time. It's a time dependent parameter where we talk about the rate at which this which is at the inherently time dependent process. Okay. So interestingly, the chemical kinetics or classical thermodynamics was developed in the same way, where people tried to explain something which is phenomenal, and they tried to develop an approach which is known as a phenomenological approach. So phenomenological approach means there are some reactions are happening, some phenomena are happening. Based on that, you have to develop a model. So where you observe a particular phenomena and you try to explain based on some logical footing. So in this same way, the chemical kinetics was also developed. But the important thing is that they might not need any fundamental understanding or the any understanding of how the microscopic world looks like. Okay. Means you can describe the entire thermodynamics of chemical kinetics in a macroscopic way. This is called the basic phenomenological or macroscopic uh, modeling, but where the microscopic modeling, microscopic understanding is not important. An example is like how a material or matter is made of. We know that matter is made up of atoms and molecules, but when you are dealing in reality, the we don't get to the atoms and molecules. We deal with the bulk matters. You take copper oxide, you take some other chemical, you take the bulk thing, which is macroscopic in nature. Okay, the similar concept also applies to the reaction kinetics. So the our understanding of the microscopic world is started with the development of quantum mechanics, and there we talk about the time independent processes. So we talk about the energetics at the energy levels of atoms and molecules. Yeah. Similarly, you could also ask how these molecules interact with themselves. For example, they collide among themselves, or how one molecule transforms into another molecule, and that is basically the basics of the chemical reaction engineering, right? So this is the time dependent process. When we talk about time dependent process, it means that we are going from the kinetic model development. Now, when we talked about the macroscopic realization and macroscopic observation, the bridge between them is the statistical mechanics. And similarly, just like we discussed the time independent process, so we can have an equilibrium formalism of statistical mechanics, where we talk about the energy levels of atoms and molecules, and then we ask uh, build up from this fundamental principle of the ab initio way of all these macroscopic variables or observables. And this connection between the microscopic and macroscopic is the equilibrium statistical mechanics or equilibrium. Sometimes we call as equilibrium thermodynamics. Okay. Similarly, you can have a non-equilibrium formalism of thermodynamics where you start with molecular reaction dynamics, starting with time-dependent quantum mechanics, and then you can explain the rates of macroscopic processes. So basically, if you see the brief history of classical thermodynamics, the thermodynamics is the only physical theory of a general nature of which I am convinced that I'll never be overthrown. It's called by Albert Einstein at 1700. You get the caloric theory, and then there's some very old the first and second laws formulation of the thermodynamics. Those were there in the 1900s. Okay. Then further, if you see the formulation of kinetic theory of gases by the Clausius, the revival of Bernoulli's work, distribution of molecular speed, the H theorem, the concept of ergodicity, ensemble approach. So there are the overall history part, and if we just keep all those things and further the law of mass action, and there's the first recipient of Nobel Prize in chemistry, which was given for the recognition of the extraordinary service is rendered by the discovery of laws of chemical dynamics and osmotic pressure in solutions. Further, the enzyme kinetics, temperature dependence of rate constant by the Arrhenius, very popular. Then the reaction mechanism, and before that the kinetics of adsorption on surface by Langmuir, and then it was extended by Hinchelwood, which we know the Langmuir-Hinchelwood mechanism, and then further it was in future it was further done by the Hugen and Watson. So it is called as the LHHW, Langmuir-Hinchelwood Hugen-Watson model for the kinetics based on the mechanism. Okay. And go to the next part, and that is important is from the properties of gases. We know properties of gases, it actually deviates from the ideal behavior, a real gas. So under pressure, gas does liquefy, even these liquids eventually solidify. Okay. So the first experiment which was done is the Avogadro's curves, compressibility factor and boil temperature. So with the compressibility factor, it is equal the P V bar by RT. So important thing is that how real gases behave. You know that ideal gas equation was hypothesized version, meaning no real gas will show ideal behavior except for the certain conditions. So the question is that what are the deviations they observe experimentally? And our real gas is pressurized. Any gas under sufficient pressures from liquid and eventually the liquid from solid. But the important thing is that the ideal gas law, which is PV equals to nRT, does not predict it if you can recall the pressure volume isotope. So what it predicts? It predicts that even at very, very high pressure region, there is no change from gas to liquid, or there is no phase transition. Okay. But the phase transition happens in reality. So the important thing is that we have to discuss the experimental facts that showed the deviation. So then using the ideal gas equation, the relationship, uh, the Maggott studied various cases and it plotted the compressibility factor as a function of pressure. So, and the plot looks like that for an ideal gas, like for the Maggott's curves, compressibility factor with respect to pressure. And the ideal gas is a straight line. Now, for different gases is proposed, and then you can see there is a deviation. Okay. So, what is happening at lower temperature? The curve was following like this, and then at higher temperature, it was going like this. So, these are the experimental curves as a function of pressure, uh, curve of the compressibility factor. If you plot the compressibility factor for same gas at different temperature, you get a very interesting behavior. These are the like T1, T2, T3. You see, this T3 is higher than T2 and T1. Okay. If you see at a very low pressure, it actually follows the ideal gas. It means you see there is a region where the curve more or less follows the ideal gas curve. It is actually known that when the pressure is almost zero, the temperature at which this behavior is observed is called the boil temperature, okay, which denotes as TB. Okay. So in this case, according to this drawing, the T2, this one, the second one is the boil temperature. Now for methane, there is a deep. If you see for the methane one, yes. So there is a deep at the low pressure, and then there is a rise in the compressibility factor. So for different gases, it actually varies. So for hydrogen, the slope is always positive. Okay. These are taken at 0 degrees Celsius. For methane, there is this dip and then followed by the rise, the horizontal straight line. The horizontal straight line is the ideal gas. The same compressibility factor, you see how it varies as a function of pressure for a particular gas. See, this is shown the example of CO2. And as you see that high temperature, The slope is positive, and low temperature there is an initial negative slope for this one. Yes. Now, um, okay. And then the Andrews experiments are done for the isotherms of a real gas. So there is this at different constant temperature. There is a PV curve and uh, the pressure volume curve at different temperature. So at the chosen five different temperatures, and T5 is the highest, and similarly the temperature lowers. Okay. If you see the isotherm activa, it look at the shape of the curve, and this is the, if you see this middle part, this one is giving us a shape of an activa. So it is a like a rectangle. So it's a A B C D, and if you see, first look at the region which is a CD region, the region at the low pressure where the very high, if you see this one is a very much high difference between two different temperature values. And if you go up, go towards the higher temperature, this difference or this region is getting smaller. Okay. So we can the equation state as PV equals to RT, but only for this region. Now if you want to change the volume by a certain amount, you have to apply a little pressure in this case. However, this is the opposite for the case of the AB, which represent the liquid state here. So the lower part is basically the vapor state, and the upper part, which is the AB, is a liquid state. Okay. That is the thing which is written here. So there is a top region which represents the liquid and the bottom part which represents the vapor or gas. So the ideal gas flow will be over only when the pressure is low, right? When you can modify notation of ideal gas, it will be valid only for the limit of very low pressure. And then if you see that uh, this okay, so I was talking about the Van der Waals real gas scenario. So what they did was to con to consider the real gas instead of the ideal gas. It took two assumptions. For example, if you consider a container, the ideal gas law will be not valid if the sizes of molecules are vanishingly small or the molecules are point-like objects. So there is no finite size for the molecules. And the second assumption is any intermolecular interventions between the two molecules were ignored. Okay, which was ignored in the um, Okay. So now this molecule is surrounded by many other molecules, and all of them are attracting this molecule. However, for a system at thermal equilibrium, this distribution of molecules inside the container is isotropic. So the molecule will feel equal attraction in all directions. There will be no net attraction in any particular or any favored direction. So if this molecule moves, there will be no change in it. It's a the velocity in a particular direction, and it will more or less obey the ideal gas behavior. However, the pressure of a gas is exerted when it strikes the wall of the container. Now let us consider when this molecule starts moving and tries to hit the wall of the container. When this molecule hits the wall, at that instant it is also attracted by the molecules which are near the surface and also by the molecules which are in the bulk or inside the container. Since the number of molecules near the surface is less than the number of molecules which are in the bulk, there will be difference in attraction, and attraction will be more from the molecules in the bulk because they are just large in number. So the speed of this molecule will be slowed down, and as a result, the molecule strike with less force on the wall or the pressure will be reduced. Now we can mathematically formulate it in order to understand that. Let us consider factors this pressure will depend on. Now the definition of pressure is force per unit area, which means it will depend on how many molecules are hitting the surface of unit area per unit time. Now this number was proportional to the density of molecules, or how many moles of the molecules are present per unit. Secondly, these molecules are also attracted by the molecules which are present in bulk. So it will also be proportional to how many molecules are present in the bulk. That number is also proportional to the density of the gas. So together, the pressure and the reduction in pressure will be proportional to the square of density, and since density is inversely proportional to the molar volume, it will eventually be inversely proportional to the inverse square of molar volume. We can write before we can write a correction for the pressure. The real pressure, which will just simply denote as P, will be less than the ideal pressure by an amount which is proportional to 1 by molar volume square, and this proportionality constant we call as A. Before A will be different for different gases. And finally, if we combine this pressure expression and volume expression for real gases and put it in the ideal gas equation, which is PV equals to RT, to replace with the real volume, PV will be P plus N square A by B square into V minus NB equals to nRT. So this pressure and volume correction will be there, and this is called as the van der Waals equation. And if you see, the main important thing is that for this kind of behavior, if you the isotherms of a real gas is the PV curve, and with respect to temperature or constant temperature, you get the isotherms, and uh, there is this kind of rectangle is formed and dome is formed where this particular difference between the two curves is actually much higher at a lower temperature compared to that at a higher temperature, and And then when you keep on increasing the temperature from T1 to T4, you will reach at a region where this particular difference, which were earlier as a line uh, distance will keep on decreasing. Finally, it will go into a just a point. Okay. So this point in the isotherm is called a critical point, and the corresponding temperature at which the critical point occurs is known as the critical temperature. So the ideal behavior is also observed above the critical temperature when the substance is present always in the gaseous form. Therefore, you can say that the ideal gas behavior is obeyed for any gas as long as either the pressure is low or the temperature is very high, which is above the critical temperature.
Hello.